Have you ever wondered what it takes to make a star literally blow itself apart with the force of billions of atomic bombs? Tonight, we're going to uncover one of the most spectacular and violent events in the entire universe. Stellar explosions, so powerful they can outshine entire galaxies and be seen from billions of light years away. But here's what might shock you. Not all stars get to go out with this incredible cosmic bang. And the reason why will completely change how you think about the life and death of stars. Welcome to a journey through the explosive deaths of the most massive objects in our universe. I'm going to walk you through exactly why some stars become supernova while others simply fade away quietly. And by the end of this video, you'll understand the incredible cosmic mechanisms that create these stellar fireworks that literally forge the elements needed for life itself. Let's start with something that might surprise you. Every single star in the night sky, including our own sun, is engaged in a constant battle. It's a war between two of the most fundamental forces in physics, and this battle determines not just how a star lives, but exactly how it will die. On one side, you have gravity, that familiar force pulling everything inward, trying to crush the star into a tiny point. On the other side, you have nuclear fusion happening in the star's core, creating an outward pressure that pushes back against gravity's crushing grip. For most of a star's life, these two forces are perfectly balanced. Think of it like a cosmic tug-of-war, where both sides are equally matched. The star maintains its size and brightness because neither force can win. But here's where things get interesting. This balance can't last forever, and when it breaks, that's when the real drama begins. The size of a star when it's born determines its entire fate. Small stars like red dwarfs can maintain this balance for trillions of years. That's longer than the universe has even existed so far. Medium-sized stars like our sun will burn steadily for about 10 billion years before they start to run into trouble. But the real monsters of the stellar world, the massive stars that are 8 times heavier than our sun or more, these giants burn through their nuclear fuel incredibly fast and face a very different destiny. Let me paint you a picture of what's happening inside a massive star as it races toward its explosive end. In the core, hydrogen is being fused into helium at temperatures of over 100 million degrees. This process releases enormous amounts of energy that keep the star shining and provide the outward pressure to balance gravity. But hydrogen doesn't last forever, especially in these massive stars that burn through their fuel like cosmic gas guzzlers. When the hydrogen in the core runs out, something fascinating happens. The core starts to contract and heat up even more, reaching temperatures where helium can now fuse into carbon and oxygen. The star has found a new source of fuel to continue the fight against gravity. But this is just the beginning of an incredible sequence of events that will ultimately lead to one of the most powerful explosions in the universe. As each type of nuclear fuel gets used up, the core contracts further and gets hotter, allowing the next heavier element to start fusing. Carbon fuses into neon and magnesium. Neon fuses into oxygen and silicon. Then silicon fuses into iron. Each stage burns faster than the last because the star is becoming increasingly desperate to generate enough energy to hold itself up against gravity's relentless pull. Here's where we reach the cosmic point of no return. Iron is special. It's like the dead end of nuclear fusion. When you try to fuse iron nuclei together, instead of releasing energy like all the previous fusion reactions, it actually requires energy input. This means that when a massive star's core becomes mostly iron, the nuclear furnace that has been supporting the star for millions of years suddenly shuts down completely. Picture this moment. You have a star with an iron core about the size of Earth, but containing more mass than our entire sun, surrounded by layers of silicon, oxygen, carbon, helium, and hydrogen, each burning in concentric shells. The core temperature is now over 3 billion degrees. Then, in a matter of seconds, everything changes. Without the outward pressure from fusion, gravity finally wins the cosmic battle it's been fighting for millions of years. The iron core collapses catastrophically, going from the size of Earth to just 12 miles across in less than a second. To put this in perspective, imagine squeezing our entire planet down to the size of a city in the blink of an eye. The material becomes so dense that a teaspoon would weigh as much as a mountain. But here's where the story takes an incredible turn. When the core reaches this incredible density, it becomes so rigid that the infalling outer layers of the star literally bounce off it like a cosmic rubber ball. This creates a shock wave that races outward through the star at thousands of miles per second, heating everything in its path to billions of degrees and triggering an explosion of unimaginable proportions. This is a core collapse supernova, and it's one of the most energetic events that can happen in the universe. In just a few seconds, this explosion releases more energy than our sun will produce in its entire 10 billion year lifetime. The explosion is so bright, it can outshine the entire galaxy the star lives in, making it visible from billions of light years away. But wait, there's actually more than one way for a star to explode, and the second type is equally fascinating, but works through a completely different mechanism. These are called Type 1a supernova, and they involve a stellar partnership gone wrong. Imagine an elderly white dwarf star. This is what's left after a medium-sized star like our sun exhausts its fuel and sheds its outer layers. White dwarfs are incredibly dense objects about the size of Earth, but containing most of the mass of the sun. Now imagine this white dwarf has a companion star orbiting nearby. If these two stars are close enough, the white dwarf can actually steal material from its companion, like a cosmic vampire slowly draining its partner. As the white dwarf accumulates more and more material from its companion, it gets closer and closer to a critical mass limit called the Chandrasekhar limit. This limit exists because there's a maximum amount of mass that electron pressure can support against gravity in a white dwarf. When the white dwarf reaches about 1.4 times the mass of our sun, something dramatic happens. The entire white dwarf undergoes runaway nuclear fusion all at once. Unlike the core collapse supernova, where the explosion starts from the center and works outward, in a Type 1a supernova, the fusion burns through the entire white dwarf almost simultaneously. The white dwarf is completely destroyed in the explosion, leaving nothing behind but an expanding cloud of hot gas and the elements created in the blast. These Type 1a supernova are incredibly important for astronomy because they're remarkably consistent in their brightness. Since they all involve white dwarfs reaching the same critical mass, they all produce explosions with very similar energy outputs. This makes them perfect cosmic lighthouses that astronomers can use to measure distances across the universe and study how the cosmos is expanding. Now, you might be wondering what determines whether a star will explode as a supernova or die peacefully. It all comes down to mass, and there are some specific thresholds that determine a star's fate. Stars with less than about 8 times the mass of our sun will never explode as supernova. Instead, they'll gradually shed their outer layers and leave behind a white dwarf star that will slowly cool down over billions of years. But once a star is born with more than 8 solar masses, its fate is sealed. It will burn through its nuclear fuel much faster, go through all the stages of successive fusion I described earlier, and eventually reach that critical moment when its iron core collapses and triggers a supernova explosion. There's also an upper limit to consider. Stars that are born with more than about 25 solar masses might not even explode as supernova. Instead, when their cores collapse, they might form black holes so quickly that not even the shock wave can escape, creating what's called a failed supernova. These are some of the most massive stars that simply vanish from view as they collapse directly into black holes. The incredible thing about supernova is that they're not just spectacular light shows. They're absolutely essential for life as we know it. Remember how I mentioned that fusion inside stars creates heavier elements? Well, the extreme conditions during a supernova explosion are where many of the heaviest elements are forged. The intense heat and pressure create elements like gold, platinum, uranium, and many others that simply cannot be made inside a normal burning star. When the supernova explosion tears through space, it spreads these newly created elements across vast regions of the galaxy. This enriched material eventually gets incorporated into new stars, planets, and potentially life itself. The calcium in your bones, the iron in your blood, and the oxygen you breathe were all created either inside stars or during supernova explosions. We are quite literally made of star stuff, as the famous astronomer Carl Sagan once said. Supernova also play a crucial role in shaping the structure of galaxies. The shock waves from these explosions compress nearby gas clouds, which can trigger the formation of new stars. At the same time, the energy from supernova can blow gas out of galaxies entirely, affecting how fast new stars can form. It's a complex cosmic cycle where stellar death leads to stellar birth. Let me share something that might blow your mind about the scale and frequency of these explosions. In a typical galaxy like our Milky Way, which contains hundreds of billions of stars, a supernova occurs roughly once every 50 years. That might not sound like very often, but when you consider that there are hundreds of billions of galaxies in the observable universe, it means that somewhere in the cosmos, a star is exploding as a supernova about once every second. The nearest supernova visible to the naked eye in recent history was observed in 1604 by astronomers including Johannes Kepler. This explosion happened about 20,000 light years away from Earth, yet it was bright enough to be visible during the daytime for several weeks. Imagine seeing a star suddenly appear in the sky bright enough to see next to the sun. That's the incredible power of a supernova explosion. Modern technology has allowed us to observe supernova in incredible detail, and we're discovering that these explosions are even more complex and varied than we initially thought. Some supernova are powered by magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's magnetic field. Others might be caused by collisions between neutron stars or between a neutron star and a black hole. We've also discovered hypernova, which are supernova explosions that are 10 to 100 times more energetic than typical supernova. These might be connected to the formation of the most massive black holes and could be responsible for some of the gamma-ray bursts we observe, beams of intense radiation that can be detected from halfway across the universe. Perhaps most remarkably, we're now able to detect the gravitational waves produced when neutron stars collide and explode. These ripples in spacetime itself were predicted by Einstein over a century ago, but we've only recently developed technology sensitive enough to detect them. When we observe both the light and gravitational waves from the same cosmic explosion, it opens up entirely new ways to study these incredible events. Looking to the future, astronomers are constantly searching for stars that might be candidates for future supernova. One of the most famous is Betelgeuse, the bright red star in the constellation Orion. Betelgeuse is a massive star that's already in its final stages of evolution, and it could explode as a supernova at any time. Whether that's tomorrow or in the next 100,000 years is impossible to predict precisely. If Betelgeuse were to explode, it would be an incredible sight from Earth. Despite being over 600 light years away, the explosion would be bright enough to see during the day and would cast shadows at night. However, we'd be far enough away that the explosion wouldn't pose any danger to life on Earth. Scientists are also using computer simulations to better understand the complex physics of supernova explosions. These simulations require some of the most powerful supercomputers in the world because they need to model the behavior of matter under the most extreme conditions imaginable. Temperatures of billions of degrees, densities greater than atomic nuclei, and magnetic fields that would instantly destroy any material object. As we wrap up this cosmic journey, I want you to think about the incredible fact that stellar explosions, happening billions of years ago, are directly connected to your existence today. The elements in your body, the earth beneath your feet, and the air you breathe all had to be forged in the nuclear furnaces of stars and scattered by supernova, explosions before our solar system even formed. Every time you look up at the night sky, you're seeing stars in various stages of this cosmic cycle. Some are just beginning their lives, fusing hydrogen in their cores for the first time. Others are middle-aged, like our sun, steadily burning their fuel. And somewhere among those points of light are massive stars racing toward their explosive fate, building up iron cores that will collapse and trigger the next spectacular supernova explosion. The study of supernova has revolutionized our understanding of the universe in ways that go far beyond just stellar evolution. These cosmic explosions have helped us discover that the expansion of the universe is accelerating, leading to the discovery of dark energy, one of the greatest mysteries in modern physics. They've shown us how elements are created and distributed throughout the cosmos, and they've given us insights into some of the most extreme physics possible. So the next time someone asks you why some stars explode as supernova, you can tell them it's the ultimate result of a cosmic battle between gravity and nuclear fusion, where the most massive stars burn so bright and fast that they're destined for explosive deaths that outshine entire galaxies. These aren't just distant cosmic events. They're the reason we exist, the creators of the elements that make up everything we see around us, and spectacular demonstrations of the incredible forces that shape our universe. The universe is a vast and often violent place, but it's also beautiful in its complexity and interconnectedness. Every supernova explosion is both an ending and a beginning, the death of a massive star and the birth of the elements that will someday become part of new stars, new planets, and possibly new forms of life. In understanding why stars explode, we're really understanding our own cosmic origins and our place in the grand story of the universe itself.